Alright, I guess let's begin. Welcome to the final lab of Chem B41, 2021, and hope you guys had a great semester. I personally am just about done with this online learning stuff. I imagine a lot of you guys are too. Very frustrating, very difficult. COVID should just end now, I think. I think we should just vote for it to end, and it should just accept democracy. Anyways, that being said, let's take attendance, I guess, first and foremost, and then we'll go from there. Just like last time, I'm just going to say the names and just we'll go into breakout groups later, and we'll go from there. So I'm just going to say your names. You don't have to respond because I'll just see you're here, because I can't read it. Oh, I've kept my chat box off just like last time. Right? So Jotham Abraham, Muhammad Ali, Sanya Anil, Huang Bui, Zayama Inam, Zaho Fang, Yanling Liang, Anjali Mahidio, Arkavan Majidi, Jiami, Jordan Morin, Zinal Patel, Alia Patan, and Parshana Singh. By the way, a lot of you guys have mentioned that your grades are up, but you can't see them. I'm working on that. Hopefully that'll be fixed soon. Right? Very, very soon, hopefully. Alright. So let's go to the next slide. Why isn't it moving? There we go. Got it to move. Sorry, there's literally, the sun has just changed, and it's like, this is like peak sunrise kind of time for me here in my time zone, and the sun literally just gets in my eyes. It's actually gotten much nicer. The weather is way nicer. The sun's much brighter. Overall, great. Anyways, that's enough about me and my great weather here. So welcome to experiment 5. Oops, experiment 5. Maybe we should start here. Experiment 5, which is the synthesis of caffeine and SN2 versus SN1 reactions. On today's agenda, we're going to talk about experiment 5 theory as nucleophilic substitution reactions, refluxing, and experiment 5 procedure. We're just going to have videos and we're going to show you, and you're going to love it. Alright, some key terms that I think is important for everyone to know. A nucleophile. So nucleophile, like ophile, is like Latin for loving, right? So nucleophile is nucleus loving, right? So they're attracted to positive charges. If you could guess, they're probably negatively charged, right? Not necessarily negatively charged, but almost all negative charges, if not all of them, are going to be nucleophiles, right? Take, for example, ammonia and H3. Not technically a negatively charged molecule, but still a nucleophile, right? And oftentimes they are electron donors, right? Which are Lewis bases, right? If you guys remember your Lewis base, Lewis acid base, and now the sun has moved here. The acid base theory for Lewis acids and bases. Lewis bases give donate electrons. Lewis acids accept. Right? So, speaking of Lewis acids, electrophiles. So, same concept, electrophile, electron-loving groups. Sorry. Electron-loving groups, right? And they are generally positively charged, as you could imagine. Right? So, H3O+, BH3, etc. Right? And the third important key term is leaving group. A leaving group is a group that is substituted by a nucleophile in a substitution reaction. That group breaks off from the main parent molecule and goes away or does something else. It leaves, to use the simplest possible term. Alright. Nucleophilic substitution reactions. Now, I understand you guys have already gone through this in lecture, so I'm not going to go over this in too much detail. I just kind of skim over some of the concepts here, and if you have any questions, I'll post my email again, and feel free to email me. And we'll go from there. Alright, SN1 reactions. So SN1 substitution, nucleophilic, unimolecular. Right? What does that mean, unimolecular? It means that only one molecule is involved in the rate determining step. Right? So that's where the 1 comes in. SN2 is substitution, nucleophilic, bimolecular type of reaction. Right? Which means that there are 2 molecules involved in a rate determining step. Right? So that's the difference between SN1 and SN2. So what you can think about is S stands for substitution, N stands for nucleophilic, and the number stands for whether it's 1 molecule involved or 2 molecules. Right? So that's what SN1 and SN2 stand for. Alright, here we have an example of an SN1 reaction. Right? So here we have a molecule with a bromine attached to it, right? With the bromine is the leaving group, right? And it's a very, very slow reaction, right? And the bromine just takes the electrons here, leaving a carbocation, which then can be attacked by ethanol, right? And then which is a fast reaction, by the way. It can be attacked by ethanol very quickly, and then you end up with a combined molecule. Right, you also end up with this positive charge is not going to last. It's going to pop off. Right, this is not going to be the end of the reaction, but this is kind of showing you what it is. Right, and here's a question for you guys: what is the leaving group in this example? It's the group that left. So a lot of you guys are probably thinking it's the bromine, and you're right. Right. So the leaving group in 2-bromo-2-methylpropane is indeed bromine. And very simply, it leaves. That's how you know. Right? And the nucleophile attacks a carbocation. Right? So these are the 2 steps. So the first step is the leaving group leaves. The second step is the nucleophile attacks the carbocation. Right? And tertiary carbocations are the most stable for resonance reasons, which I'm pretty sure you guys have probably gone into. And back to my eyes. The sun, I mean. Alright, so here is the energy diagram of an SN1 reaction. Excuse me. 1 second. Alright, so here we have our 2-bromo-2-methyl propane. I think that was the molecule's name. 2-bromo-2-methylpropane. Yep, that's right. 2-bromo-2-methylpropane. 2-bromo-2-methyl propane. There we go. Sorry. Right, so here we have our molecule, and the first thing that has to happen is our molecule has to go all the way up, and it requires energy for it to end up at this position where it can lose the bromine and form the carbocation. Remember, carbocations are not stable, so you want to leave quickly. Right? And it's this long uphill battle, which is the rate determining step. Right? And the rate of the reaction depends only on the substrate and not the nucleophile, because if you look at the reaction mechanism again, right, this is a very slow step that's super fast. I mean, technically speaking, they both take up some amount of time, but because this is so much slower than this, if you were to try and quantify it, you're going to end up with like 0% in like change with this. It's so much faster, like a million times faster or something. Right? But it takes a lot of energy to pump that bromine out, right? So to get rid of the nucleophile. And yep, they're just showing you that first the bromine has to leave, the carbocation forms, then you get attacked by the OH group to get your molecule. Here instead of an ethanol, it's just an acidic condition, but sure, same concept, right? I hope that's clear. It's very simple. First you pop off the bromine, right, which is the rate determining step. It's slow, it requires a lot of energy, right? Then you can have a quick reaction with the hydroxide group, right? And then you end up with a slightly different lower energy for your molecule. Right? The molecule should end up at a lower energy level. If it ends up at a higher energy level, then it's gonna go backwards, right? All right, SN2 reactions, right? SN2 are one-step reactions. They're not two steps. So this is where it gets a little bit confusing. SN1 reactions have two steps. SN2 reactions have one step, right? A little bit difficult to kind of grasp, but if you just remember that the numbers only correspond to the number of molecules involved, I think it should be okay. So that's how I do it and prevent myself from getting confused. I remember it only has to do with the number of molecules, and the more molecules you have, the fewer steps you're going to have. Not because you can't have so many molecules, like, do it at different times. So anyway, so SN2 reactions are one step. You have your nucleophile attack the carbon, right? And you have the leaving group leave, right? The electrophile leave, right? And this all happens at the same time, right? The nucleophile attacks from the backside and the leaving group leaves at the same time. So here's a question you guys might be wondering. Why does the nucleophile attack from the backside? Right? Why? What's the point of that? Well, this is a concept called steric hindrance, right? The bromine, although not shown here, is actually much bigger than the hydrogens. So if you were to think about the overall structure, so if these are like three hydrogens, right? And you have like the fourth one over here, that this bromine is gigantic, whereas the space from these carbons is much less. Like they're tiny hydrogens that are attached versus a giant bromine. Not only that, the bromine is going to be slightly negatively charged. It has a higher electronegativity, and so it's going to repel the OH group. Right? Couple of things there. Okay? And again, for SN2, there will be no intermediaries formed. So what will the energy diagram look like? It looks like this, where initially you have your your reagents, then you have this weird phase where you have multiple things attached, right? And you have the OH on the one side, the Br on the other. Both of them are slightly negatively charged, right? And eventually your reaction will continue with the bromine popping off and the hydroxide group staying on, right, to form methanol. Right? So you might be thinking, what are the main differences between SN1 and SN2? Or even if you're not thinking, you're probably reading it, because I think that's the question is, right? What is the main difference? Yes. Right? So so a couple of differences regarding their energy diagram, because we can see it clearly on the board here, right? We can see, number one, the SN2 reaction only has one hump. SN1 had two humps. Right? And so that's a major difference, and that corresponds to the number of steps in the reaction. Right? The second difference is that in SN1 reactions, the rate determining step is the removal of the leaving group. Right? Attack by the nucleophile occurs later in the second step. The rate determining step is determined by only one group. Whereas in SN2 reactions, it's determined by both the substrate, like the leaving group, and the nucleophile. Right? So both of them play a role. So those are some of the differences. Alright, what are we going to be doing in this cool lab? Well, we are going to be doing, we're going to be converting theobromine to caffeine via an SN2 reaction. So you're thinking, SN2, one step, no intermediary. You're right. That's indeed correct. Right? So first of all, theobromine is deprotonated using an oxygen or methoxy group. Right? Using a methoxy group. Right? Forming a strong base and nucleophile. And if you're wondering, yes, I haven't actually prepared for this lab per se. I've done it before, so that's why I haven't done it. But anyway, so you have the methoxy group that attacks the theobromine. Right? Which results in the removal of the iodine. over here, right? So methyl iodine will lose its iodine because, okay, so this is an SN2 reaction. I'm not sure if I'm overcomplicating this because you guys already have studied this. It makes sense to you, right? And then I don't have to try and explain it so quickly. So what's going to happen is you have theobromine, right? And what you want to do in order to get caffeine is you want hydrogen. That's pretty much all you want to do here, right? And then you have caffeine. So how are you going to get rid of this hydrogen? You're going to get a methoxy group to convert the theobromine into a very strong nucleophile, right? And it's interesting that the nucleophile is actually the compound we want. So this is a little bit about the creativity that chemistry can allow for, right? So the nucleophile is the compound we want. So the methoxy group attacks the hydrogen and takes it, giving so the electrons go to the nitrogen, making it negatively charged. If you have sodium ions, because the methoxy group came from somewhere, right? So let's say it's a sodium methoxy you've added, right? The sodium would be attracted to the negatively charged nitrogen, negatively charged. It's going to attack the carbon in methyl iodide, attack the carbon in methyl iodide, and this is the actual reaction we're talking about. That is the SN2 reaction, right? And the iodine pops off. This is not the SN2 reaction, this theobromine to caffeine. That's not the SN2 reaction. The SN2 reaction is the conversion of this intermediary or this ionized theobromine into I lost my train of thought, but basically we want to convert this. This is the SN2 reaction we're working with. We're going to convert this hydrogen here to a methyl group through these means, right? By converting it first to a nucleophile, which is then going to attack the methyl iodide, and you're going to go from there. Hopefully that's clear. Refluxing. So refluxing is used whenever you want to speed up a reaction because increase in temperature increases the reaction rate, right? Because it gives it energy to get to that first hump. Remember the first hump in the energy diagram? So that's where heat comes in. But it also, because the reflux the reflux tubes are quite long and they're cooled, so that even though you're heating it, the vapor isn't escaping. Right, so that's the purpose of refluxing, and we're going to be using it in this lab, as you will see in the videos. Procedure. Alright, so we're going to see the procedure, but we'll talk about it here in just for a minute. So we're going to get a 50 ml round bottom flask, add boiling tips, add boiling tips and put it on a hot plate. Right? You're going to mix 0.10. That is the weirdest way to say it. 0.1 grams of theobromine, 3.0 mils of methanol, and 0.06 grams of sodium methoxide. Right? So these are going to be your three compounds. You're going to mix them together. Right? And then you're going to add 1.2 mils of methyl iodide, right? And transfer into the 50 ml round bottom flask. Right? And boiling tips are important because you want to have an even heat. You don't want things to explode. So here's a question for some of you guys. Why do you want to add everything else first and the methyl iodide later? Well, this would ordinarily be where I would interact with you guys, or actually ordinarily I would be yelling this to you guys in the lab and you guys would be doing it hands-on and it'd be great, we'd all be loving it. But anyways, I'm just going to answer. Why? Well, because you want to give ample time and you want the reaction to start. Right, so you need the methoxy group present in order to ionize the theobromine, right, which is then going to attack the methyl iodide. Right, so you want to have it ready beforehand. Right? And you don't want the methyl iodide to start to become attacked by the sodium methoxide or anything like this. And hint, SN2 reaction, and the reason why is because you want to get ready for the SN2 reaction, because the SN2 reaction will require both the methyl iodide and the ionized theobromine in order to work. So you need both at the same time. If one of them is lacking, for example, a theobromine hasn't ionized, then the reaction won't go. Alright, then you set up the reflux, right? And you reflux for 1 hour. After reflux is complete, you'll boil off the solvent, and then you'll add 5 ml of DCM to the round bottom flask. The DCM, by the way, is highly nonpolar and will dissolve any nonpolar compounds. Alright, let us begin. Okay, so here's where things are going to get a little bit crazy, because there are like 7 videos I'm going to show you guys. And I've already got them here, so we're going to hope that everything works great. I'm going to raise my volume just to make sure you guys can hear everything. Actually, I can put on my headphones. Alright, here you go. So we have quite a few of these. And hold on, I think the volume's off. Hold on, I'm gonna turn this off. You guys can hear me. I think there's a volume problem, but I'm not even sure if there is volume, to be honest. Okay, there's no volume, so you're not missing much. So it's just showing you all of the compounds, the glassware, all that sort of stuff. Here is the final bag and everything you're going to put in. More equipment you're going to use, rubber bulbs, a syringe, the TA fume hood that'll have all of the chemicals in it, hot plate, everything nicely labeled. This is the weighing scales, the analytical balance. So 0.06 grams, you're probably going to want to use an analytical balance for that. Alright, that was the first. Second step. So here we go, second step. Here we are cleaning the analytical balance. You want to make sure that it's calibrated, so the circle should be in the, like there's a bubble, and that bubble should be inside the circle. It just means that the scale isn't like tilted or anything, right? It's just, it's flat straight. So tare it, add your RBF. You're going to weigh your compounds. Hold on a second. I think for this portion, I don't particularly need to have my thing on, so I'm just going to turn off my... Actually, I might as well just... Why didn't I give it to you guys full screen? There you go. Sorry, you guys didn't see it full screen before. I think the videos are pretty self-explanatory, so I'm just going to let them go on. Alright, so that was weighing all of your compounds. So here we're going to dissolve the compounds. Sodium methoxide and methanol. I think it's very straightforward. I'm just going to let you guys watch. Remember the meniscus, you gotta make sure that the bottom of the meniscus is what matches, right? Shaking hard to make sure you dissolve it all. So we're adding every portion of that to the round bottom flask. So the sodium methoxide has been dissolved in methanol and transferred to the RBF. Iodomethane is being added now, using a syringe to make sure you get the correct amount. Right, so making sure to gather 0.6 ml exactly. Add another 0.6 ml aliquot. Oh, the reason is because I don't think this is a 1 ml syringe. It doesn't have 1.2. Otherwise, if you had a larger one, you could probably get all of it at once. But anyways, he's doing his best, and that's what counts. Boiling tips. Alright, so that is us adding all of the components together. Time for reflux. So, hold on. So they're showing you that they added the grease around these things because students often forget to add the grease, and when they do that, then the round bottom flask will get stuck to the components and then it'll break. So they'll actually put the grease inside this syringe and they're going to add it from there. Super cool idea. I would just use my gloved finger and just go around it once, but pea drop size. I thought that was kind of interesting. So whenever you guys start doing these sorts of experiments, you'll notice that they attached everything and then moved the hot plate up. So that is a good way to do it. That's how I would recommend you guys do it. Also make sure to clamp the round bottom flask and anything that attaches to it at the point of attachment, otherwise things could break. Again, you want water in, right, and then water out so that it fills up the whole thing. What's going on? You have your condenser, tubing. Remember, water in fills up, then water out. Yep, water in is at the bottom, it fills all the way up, then comes out. It's very important, that way it fills up. If it happened the other way, water would be coming out before going in. So here we can see the reflux stream, which is the vapor, right? We don't want the vapor to go too high, we want it to stay near the bottom. It's condensing back in, that's important. Alright, next up, boiling off the methanol. Okay, so once the reaction is done, you want to get rid of the methanol. So 1 hour of reflux is now complete. Alright, then you remove this, now all the solvent is gone. You can really easily check. See, you can see, like, there's no solvent left. All methanol is gone. Now that the methanol is gone, we go to the next step, which is reconstitution and extraction. So we're going to use DCM for that purpose. DCM actually is very volatile. I think its boiling point is like 30 30 degrees Celsius, something like that. So I would just leave some DCM on the thing, on the counter, it will evaporate. So it's very easy to get rid of. Hold on, let me check to make sure I'm saying that right. DCM doesn't evaporate, does it? It does, yeah, okay, it does. It's about 40 degrees, though, not 30. There we go. We're going to add it to a separatory funnel so we can separate the aqueous layer from the organic. I kind of want to focus here for a moment. Look at the way they grip it. Gripping it with two hands all the time, making sure to cover the cap, very important. Pointing away from yourself into the fume hood in case something horrible happens, it doesn't hit you or your friend. Right? And swirling hard. Like, it's not like gentle swirls, it's pretty hard. Now just let it settle. So usually we have the case that the aqueous layer is more dense than the organic layer, right? Because water has a density of 1, whereas ethers and stuff have a density of like 0.7, right? Or 0.7 or 0.8, right? In this case, DCM, I believe, has a density of 1. I'm going to guess it, 1.4. 1.33. I'm off again, but only by a little bit, right? 1.33. So it's actually more dense than water, and it's very highly hydrophobic. Right, so anyway, so the organic phase is on the bottom, very cloudy. And making sure to get, okay, this is important, they left a little bit of it in there still, so they're not fully done. Right? So they're going to add a little bit more DCM. So why would they want to do that? Well, one of the reasons is because they want to make sure they wash all of it away. So they got rid of the bulk of the DCM. Now they're going to add fresh DCM and also go through obviously the round bottom flask in order to make sure that they dissolve all of it. If you guys do analytical chemistry, you'll see why 3 washes are used, right? There's like this really great experiment they do with, I think, grape juice or something like that, and it makes a lot of sense. After 3 washes, you can see that you've removed over 99%. Alright, next up. Uh-oh. Oh no. Okay, good, hold on, we're good. So we've removed the aqueous phase, right? So we're going to dry and decant now. We've removed the organic phase, I'm so sorry. Right? We're going to add anhydrous sodium sulfate. That'll remove any water that might be present. Remember, caffeine is a very hydrophobic molecule, right? So it's going to be in the organic phase. Once it's done, the dried amount, you put it onto the pre-weighed beaker. So I'm going to pour it in. And as I mentioned, DCM will just evaporate even if you just leave it at room temperature on the bench. So they're making sure to decant. They don't want any of the solid stuff to get in there, right? That sodium sulfate, you don't want that. And notice how the sodium sulfate is, you know, it's not like a mush, which means that there's not a lot of water in there to begin with. The boiling tips, because they don't want to just leave it. Right, they're going to heat it up. Sorry. I keep forgetting to put it on full screen. Alright, everything is nice and dry. There you go. I'm actually going to go back and let you guys... No. You guys are going to get real values from the professor anyways. Alright, so there you go. That's the dried. This is the melting point. So you've seen this before. So hopefully there's nothing new. There's no sound in any of this, by the way, guys, so don't worry. There you go, melting point. Feel free to write down. Almost done, guys. Cleaning up. Maybe I should put my camera back on. Okay, now I'm going to keep my camera off. Alright, all done. Now you guys know how to synthesize caffeine because you've watched videos on the matter. Don't worry guys, it seems like you didn't learn much, but I'm sure you definitely did, and once you get into the lab, whenever it happens, they'll definitely make sure to train you. So don't worry about if you feel like you're missing out or anything. You're definitely not. Alright. So, we are actually way done because we didn't wait for all this stuff. What's this? Oh, transfer to the separatory funnel. Stuff like this, which is the organic layer. As I mentioned, the organic layer is the bottom layer this time around because of the higher density of DCM. Extraction, drying, decanting, evaporation, melting point, termination, cleanup. Very important step, cleanup. I often am near the end of labs, and I kind of miss this now, but I used to yell around, there are 15 minutes left, you must clean up your desk or your fume hoods, otherwise you will lose marks. That's great. Great times. Anyways, SN2 reactions. Effect of substrate structure. Okay, so there's actually something else that's going to go on, and I think this is a separate experiment. So you're going to add 2 mL of sodium iodide to 3 test tubes, and 2 drops of 1-bromobutane to the first, then 2 drops to the second, and 2 drops. 1-bromobutane to the first, 2-bromobutane to the second, and then 2-bromo-2-methylpropane to the third. Right, and you're going to look at the effect of structural difference. What structural differences make? These are all very similar compounds, and don't worry about the actual structure. You'll see it in a minute. Right? And you're going to record the time it takes for precipitation to occur. Alright, video time. Okay, I'm going to close this. Yep, close all of them. So I wasn't able to download these videos this time around. I just wasn't given permission. Like, it wouldn't let me online. So that's why we have to depend on my internet connection here. But I'm sure it's working out pretty well today, I think. So, effective substrate structure. So here we go. We're doing literally what I just said. Yeah, and make sure there are no air bubbles because air can react. Go, just about to add it. Alright. 2 bromo, 1 bromo, 2 bromo, 2 bromo propane. Excellent pipetting skills being used. Alright, they set the timer. Alright, observations. So 1-bromobutane, pretty cloudy. Right, reaction has occurred. You can see the precipitate, you guys see it? Floating in there? Okay, if you don't see it, I can tell you. 2-bromobutane, didn't happen, pretty clear. 2-bromomethylpropane, still didn't happen. Back to the reaction wasn't able to go on. Let's look at this for a second. What does it say? Part 1, effects of substrate structure. 2 mils of that, solution cloudy after 3 minutes, precipitation observed after 4.5 minutes. So maybe something you guys might want to write down. Okay, I think you guys probably wrote that down. The others did not react. So we noticed that the least bulky group, right, the 1-bromobutane, had the simplest, or had the greatest reaction. Let's continue. Clean up. Liquid goes into liquid waste, solids go in solid waste. All solid wastes go into the green bin. And halogenated wastes go to the halogen waste container. Excellent, and gloves go in the gloves bin. Alright. Back to our presentation. I'm just going to keep my camera off because there are so many videos and stuff that I don't think I even need to be shown. Anyways, next up, effective steric hindrance. So we looked at structure, now we're looking at steric hindrance. There you go. Same concept as before. Except now we're comparing 1-bromobutane to 1-bromo-2-methylpropane. So here's adding to the 1-bromobutane. Filming it up so stuff doesn't evaporate. Alright, observation. So the 1-bromobutane, you can see that it has some precipitate. The 1-bromo-2-methylpropane, nothing. Just dust, not precipitate. And we'll pause here for a second. Or not. Okay, sorry. I meant to pause. It didn't pause. There you go. So 2.5 minutes became cloudy, 4 minutes precipitate. I'll give you guys a couple seconds to write that down, or take a picture. Alright. Next up, we're going to look at the effect of leaving groups. So what happens if you have different leaving groups? I'm not even going to go back to the slide, but that's what the next step is. Everything we need will be mentioned in the video here. So here they're just draining everything. They're gonna add it. Start the timer. So very slight maybe a little bit precipitate. Yeah, okay, there it is, lots of precipitate. And nothing. Nothing at all. I don't know why they don't clean their tubes first, remove the dust. And I'll let you guys write this down. Solution became cloudy after 40 seconds. The other one, in 2.5 minutes, you could see precipitate. And I'll give you guys a couple seconds. Feel free to take a print screen or whatever. Alright, next up. Alright, and finally the effect of substrate concentration. So it's the same compound, just different concentrations. A little bit cloudy. You can see precipitate there, so 2 molar, you can see more precipitate. So, hold on, it never works. Sorry guys. Let me go back here. There we go, that's what we want to see. So, the lower concentration of 1 molar, it took 2.5 minutes for it to become cloudy and 4.5 minutes before precipitation was observed. Whereas for the 2 molar, it took 1.5 minutes for a solution to become cloudy and 3.5 minutes for precipitation. So, as you would have probably guessed, increased concentration, increased reaction. Alright, so I think we're done with this. Close. Yep. No, don't exit. Oh, sorry. So yeah, we went through all of these. SN2 effective leaving group, substrate concentration, we just saw that. Alright, things to do before lab 5. Review appendices for extraction and reflux. This is all stuff you should do beforehand. And good luck on your lab, your last lab. Don't forget there is a lab test. Right? So this is actually stuff you were supposed to have done beforehand. Right? But I'm sure you've done it. And the most interesting thing here, I think, is that there is a lab test. Right? And I will get you guys information on the lab test in a little while. But yes, indeed, there is a lab test. Right? And before you go, there's something I need to tell you. A message from the professor. Here we go. Okay, so I'm just reading the email here. So, do not write down the values you saw in the videos on your sheet, your data sheet, right? You're going to have to go onto an Excel file, and the Excel file is going to give you separate predictions, and all the data will be in an Excel file that you have to use, right? So do not use the numbers and the values you saw in the videos. You're going to be using the values given to you in an Excel file for this lab. So generally speaking, SN2 reactions are faster for primary cations. All of the stuff you just saw in the previous videos, higher concentrations, faster reaction rate, these sort of stuff, right? And just to make sure that's clear, just so you're aware, SN2 reactions are faster for primary carbocations, then secondary, and then hardly occur for tertiary. Right? And so I'm not supposed to give you guys any more things so that you can make your own predictions for the set of molecules that you will be given. Alright, so here's what's going to happen. You're going to get a data sheet, and in that data sheet you're going to have to make predictions. One thing that is missing here is your breakout groups question. Whoops. Let's make it now. Wow, cannot spell. And your question will be, what is the difference between SN1 and SN2 reactions? ENC. Right, so you're going to go into your breakout groups, and then I'm going to give you guys about 5 minutes, then you're going to email me. So hopefully that works. And I think at this point we are pretty much done the lab. You guys all probably have questions about the lab quiz, which I need to find out about. The lab test, I mean.